I realized because I have to do the mic and the clicker that I can't drink my beer at the same time. Which I know, right? So enjoy it while you're sitting down. All right, well, good evening, everyone. So I'm here to tell you about the science of Star Trek, which, as you can see from this diagram, doesn't show up on the thing. All right, well, right, we'll click. So a lot of people, I feel like, when they think about the science of Star Trek, envision something like this scene. Let's see if this works.
Enterprise computer system controlled by three redundant is based on an FTL processor with 25 bilateral telemetry modes, inflamed primary hydrogen.
All right, well, that only worked okay. I'll tell you what the joke is supposed to be. So the joke there was that was one of the characters from The Next Generation, and he's using all this like insane technobabble to one of the aliens. And it's actually a joke in the show. He's just saying these completely nonsensical words. But that's a lot of the way that people view the science of Star Trek. It's this sort of insane technobabble of like verteron particles and whatever, right? Right, dilithium, exactly. Trilithium? All right. But so actually, I'm going to do a little bit of a defense of Star Trek and the science of it to begin with, because if you think about when it came out, right? So the original series of Star Trek came out in the 1960s, and the quality of TV science fiction at the time was Lost in Space, which I sort of tried here to find the goofiest picture I could. But it's pretty much just a show that's got like a robot, it's got a kid, it's got the mom and dad, and they're flying through the galaxy, and they go on, shenanigans and adventures, and it's something like they're breaking rockets, misfire, and they end up on the other side of the galaxy from Earth. So the other side of the galaxy is like 100,000 light years away. That's the equivalent of saying that you're riding a bike and you take a wrong turn in State College and somehow you find yourself on the streets of Beijing. So the science in Lost in Space was not great. And a lot of actually the design and scripting of Star Trek was in a response to this, in a response to the science fiction that was on TV at the time. And it was trying to be something that was realistic is not quite the right word because it's a show set in 2265 about a bunch of people on a spaceship, right? But more reasonable and closer to scientifically accurate. And if you know the units that astronomy likes to use for distance, like parsecs and astronomical units instead of light years, those actually show up in the show. Like they have people who knew a lot about astronomy who are vetting the scripts and gave them information. It isn't perfect, right? You have to make a TV show and the plot comes first, but a lot of it is much better, particularly than what was on at the time. Okay, so the first part in the science of Star Trek, I'm going to do two sort of topics. Both of them relate to the famous phrase, to boldly go where no one has gone before. That if we're going to go boldly, first of all, how do we actually get there, right? So the nearest star to Earth is Alpha Centauri and Proxima Centauri. There's three stars that are all orbiting each other. Those are about 4.3 light years away from the Earth. That's the closest star to the Earth. Everything else is much farther away. It's tens or hundreds of light years away. Even some of the real stars that they go to in the show are hundreds of light years away, right? So how do we get there? The problem is that even the closest star, Alpha Centauri, is extremely far away from the Earth, right? If you're going there at walking speed, which you'd never do, it would take 1 billion years to get there. Apollo 10, when they left Earth orbit for the moon, they were the fastest humans ever, going at about 25,000 miles per hour. It would take them over 100,000 years to get there. The fastest thing humans have ever made would still take 75,000 years. And light, the fastest thing in the universe, takes about 4.3 years, right? So all these timescales, I'm going to posit, are too long for a 45-minute show. Right? We need some faster way of traveling around the universe. And so it's a TV show, right? We can just do whatever we want. So Star Trek says, terrific, we're going to go warp speed, right? if you really want to get start like Trekkies going, ask them which warp speeds correspond to which velocities. I think we can all agree that warp 1 is the speed of light, but what happens after that is it's a whole bag of cats. That's a fun discussion to look up on the internet if you have a free moment. Okay, I'm just going to stop though before we get into warp speed. I'm actually going to describe an idea that sort of is going to work, but I'm going to stop and say that just generically, anything that allows you to travel faster than light is impossible, right? This comes up a lot in science fiction because a lot of science fiction books and TV shows and movies, we don't want to spend several hundred years getting to the nearest star. We want to be able to jump around, we want to be able to fly around, we want to be able to have adventures. And so there's all sorts of ways that people travel faster than light, but generically it's all physically impossible, right? And the problem is that if you get anything that allows you to travel faster than light, you can cause something called causality violations, which are pretty much, you can get in situations where cause and effect are reversed, right? Where I can shoot someone and they will get shot before I pull the trigger. So the question is, if that happened, what happens if I don't pull the trigger, right? Does the universe collapse in on itself because I've now created some sort of paradox? So physics operates to prevent us from being able to do that. Causes of things always have to precede the effects, and if you could travel faster than light, that wouldn't be true. Okay, but there is actually an idea that's weirdly enough was based on Star Trek. So Star Trek, when they created the warp drive, it was a name, right? They're like, terrific, we have a warp drive, it lets us go really fast, right? What happens, though, is that all the physicists and astronomers watch Star Trek and start thinking, well, how would we try and get a warp drive to work? And then try and figure it out. And so the idea that people have come up with is that you don't actually travel faster than light. What you do is you actually make space move. Like normally when we're traveling, we're moving through space. As I'm walking across the room, I'm moving through space, right? So the idea to travel faster than light is instead of moving through space, you get space to move underneath you. You contract the distance in front of you and you expand the distance behind you, right? That's actually literally a warp drive, warping space underneath your spaceship, and you're using that to travel. And at no point do you actually travel faster than light locally, but because of that contraction and expansion, you can appear to move much faster than the speed of light. So that's the idea, right? It's called an Alcubierre. I've never actually had to say this word out loud. Alcubierre? Does anybody actually know how to pronounce this?
Alcubierre.
Alcubierre?
Spanish.
All right. That's not part of the trivia, is it? The pronunciation? Or is it? Right. For the record, I've been told that I cannot participate in Star Trek trivia, which I think is a real bummer. But yes, it is a Michael Alcubierre. Came up with this idea, right? He worked out the mathematics of it and proved that it could work. Here's a nice little demonstration. We're contracting the space in front of us, expanding it behind us. I should say that the press loves this. This comes up every couple of years. Somebody writes a paper on it, and the newspapers sort of lose their minds about how NASA's working on warp drive. We're all going to be traveling to other stars, and et cetera, et cetera. And you get these very nice looking graphics, right? That looks very real. So there's a lot of people online who are like, so have we actually built this thing yet? Like, what's happening? Interestingly enough, you notice they named it the Enterprise. The problem is that to get this to work, you need something called negative matter, which is pretty much, so Earth, everything we know about is positive matter in the sense that it has gravity that is attractive. Gravity attracts things towards it. Negative matter is something with negative gravity, something that if you had a Earth made out of negative matter, everything would be repulsed away from it by negative gravity, right? You need some way to expand the space behind you. And the only way mathematically we can think of doing that is something called negative matter, which in principle doesn't violate any laws of physics to exist, but nobody's actually ever seen it. So that's one problem with this idea. The second problem is that the power requirements would be huge, and huge is a huge understatement here. So a working drive like this would take about 10 billion gigajoules worth of energy to launch you on your way. That's the equivalent of the entire electrical production of the world for a year. So I actually looked at when I realized this, I was like, well, that's actually a lot more reasonable than I thought, right? We just put it all into a battery for a year, right? The problem is that storing that much energy right now is impossible, particularly on some sort of ship. You got to take a year's worth of electricity production, jam it down into something the size of this room, and then put it on a spaceship. Star Trek gets around this because they can. They just say, great, we have a reactor. They actually, interestingly enough, the way the reactor works is actually the way you do this. Right? If the way you wanted to do this, actually generate this much energy, is you'd use matter and antimatter. So I was just talking about negative matter. There's also something called antimatter. This actually exists. We can make it in particle accelerators. It's sort of the opposite of matter, and when matter and antimatter collide, they turn completely into energy. It's the most efficient reaction that we know about. So in Star Trek, that's how the warp drive works. That's how they power the warp drive, is they have antimatter, and they react it, and that generates the energy they need. You don't need a huge amount, relatively speaking, of antimatter. You need about 1,000 pounds of antimatter, 1,000 pounds of matter. If you put those two together, you get that much energy out, right? Okay, great. We need like a ton that goes on our spaceship of our fuel. That seems pretty reasonable. The problem is that currently getting 1/10 of an ounce of antimatter costs about $10 trillion, and we can only store that for a fraction of a second. So storing hundreds of pounds worth of antimatter, even producing it, just go on.
I don't know. I hate to switch.
We need batteries.
No? Okay. Yeah, maybe it. All right, we'll see if the stays on. Right, yeah, I know. A tiny antimatter powered microphone. I don't know if I'd want to be standing next to it. Antimatter reactions produce a lot of radiation. So anyway, so you need a lot of antimatter. So in principle, something like a warp drive is possible, right? If we have negative matter, we've never actually seen that, but it's in principle possible. We need to discover that, gather it, put it in our ship. We need to figure out a way to make antimatter. To a certain extent, those are, we'll call it engineering problems, right? There's no real laws of physics that are being broken, even if, as a practical matter, it's probably impossible. Right, okay, so the second part is, okay, now we figured out how to get there, right? We're going to get to the star using our warp drive, using our negative and antimatter that we've discovered and produced on Earth and not blown ourselves up with. And the second question is, when we get there, what exactly do we do there? And by that I mean, how do we get down to the planet's surface? And the Star Trek solution to this is a transporter. Like this teleporter that you step into, it beams you down and you materialize on the planet's surface. Interestingly enough, the reason why this was written into the show is not because they had some, verb for teleportation. It's because they couldn't afford to make the sets for like shuttlecraft and other ways to get down to the planet. So they were like, all right, well, they'll just materialize and teleport, and there, it's cheap. So the transporter was invented. And before I go into sort of the mechanics of how whether or not a transporter would work, it's interesting to think about how a transporter works, right? So you step into it, you dematerialize. You're blown apart into your constituent atoms or whatever. They're then fired across space. They come to the planet, and you're reassembled on the surface of the planet, right? So it's interesting to act in that process, right? I've been completely pulled apart, vaporized effectively. Is a transporter some sort of like diabolical murder machine that kills everybody who steps into it? Right? Another way of thinking about it is the person who steps into the transporter the same person who steps out? The show really goes back and forth. The show actually, if you pay attention, they periodically have episodes where they have the transporter do things. Like the transporter, it turns out, can cure any disease that anybody receives. They used that in one episode, realized that's a horrible idea for plot reasons, and never mention it again. In this one, they created a duplicate of one of the main characters. This guy lives like 10 years by himself on a planet, sort of like a Robinson Crusoe situation. So apparently you can also just duplicate people using a transporter. They never use that or come back to it. So, right, is this person who walks into a transporter the same person who walks out? That's another good thing to Google. That's another, if there's one thing I feel like the internet is good for, it's really detailed Star Trek discussions, including, okay, so how would the transporter actually work? An interesting way to think about this is just think about the information we have to record, right? If we want to dematerialize me and rematerialize me something else, we're going to have to record me as a person, store that information, and then transmit it down to the planet's surface, right? So you can say, okay, what are the basic building blocks of people? The basic building blocks of everything are atoms. So what do we need to record to get the information for one atom? And you need sort of 7 numbers. You need 3 positions, 1 for each direction, 3 speeds, the velocity in each direction, and you also need an energy level, how sort of hot the atom is. So we need 7 things. That takes up about 200 bytes worth of information. For anybody who's programming, that depends on what precision floating point numbers you're using. I had to look this all up this afternoon. So I don't actually just know this off the top of my head. But it's about 200 bytes, right? So great. 200 bytes, that's pretty reasonable. That's a small, very small fraction of my cell phone storage, right? So great, we can do an atom. All right, let's go up 1 notch. A molecule. So people are mostly water. So what will we do for a water molecule? Well, that's 2 hydrogen atoms, 1 oxygen atom. That's 3 atoms, so that's about 600 bytes. That's still pretty small, right? That would even fit on one of the old, like 5.25 inch, 5.5 inch floppy disks pretty easily. But water molecules are pretty small. You can imagine, okay, next step up for a person is a red blood cell, right? What would be, how much would we have to store for a cell? And this is where it starts taking off. So a red blood cell contains about 10 trillion atoms, right? There is a lot going on in a red blood cell. So to store a red blood cell, you would need 20 petabytes worth of computer memory. And a petabyte is 1,000 terabytes. So sort of the largest single hard drives you can buy today are 10-ish terabytes. But you could do it, actually. So the consensus from people who sort of do this sort of stuff on the internet is that Google, Microsoft, and Amazon and Facebook are probably storing about 1,000 petabytes worth of information on their servers, right? So this is actually like a reasonable amount of information. You could get a bunch of red blood cells, record everything you needed to know about them so that you could transport them using current technology. It would be hard, but we could do it, right? Facebook is doing this right now using all of our pictures and personal information. But to go to a whole person, right? So red blood cells have 10 trillion atoms in them. The real problem comes in that people contain 10 trillion, roughly, red blood cells, right? So recording a whole person, recording me, is going to take about 1 billion exabytes, which is 1 exabyte is 1,000 petabytes. So 10 trillion times the amount of storage. For reference, all the computer storage in the world is about 300 exabytes. So we need, I don't even know, what's 1 billion divided by 300? That's a lot, right? It's like a 10 million? Am I doing that right? 20? 20? Who said 20? Anyway, it's way more computer storage than exists in the entire world. And you can say, well, Star Trek takes place 200 years in the future. They literally have computers that seem to be artificially intelligent. This is like a complete side note that I didn't include here. But the computer does seem to be artificially intelligent, but it's effectively like enslaved that only does whatever they want it to. That's never talked about. I feel like it would be an interesting episode, like the rights of the computer. Anyway, they have this amazing computer that can do pretty much whatever you want. So maybe 200 years from now, we have the capability to store, 1 billion exabytes in a transporter pattern buffer and can store this information. At that point, you run into a physical problem, which is the Heisenberg uncertainty principle. So I've talked about what we need to do is we need to record the position and the velocity of every atom within my body. The problem is that's not possible to do. There's something called the Heisenberg uncertainty principle, which I can I don't have time to describe the quantum mechanics, but effectively, because of quantum mechanics, you can either know the position of an atom or you can know the velocity of an atom at one time. You cannot know both simultaneously perfectly. It's something that's very different from the regular world where we can know position and velocity at the same time. You can see me walking, you know where I am, you know how fast I'm going. You couldn't do this with an atom. If I started walking like this, my position would like spread out. I'd become fuzzy or something. So this actually is the physical reason why a transporter never could work, is because the Heisenberg uncertainty principle would make it impossible to measure the position and velocity of all the atoms in a human body precisely enough to actually store somebody and teleport them. Of course, all the science work, right? Because it's never going to work, because we need to write a book, we need to tell a TV story, we need to tell some sort of story, and we're going to bend the rules of physics and engineering so that we can make it interesting, right? The real point of science fiction is not, do we get all the science right? It's sort of, what's, one idea from today? Like if computers suddenly became intelligent, what would that mean for society? What would we have to do, right? It's really a way of exploring the issues of science and technology in our lives in a setting where you can sort of extrapolate it out to its logical conclusion. So, to a certain extent, this getting the science right is important and good for these sorts of shows, but is also a little bit secondary to the ultimate goal, which is really examining sort of the issues that we're facing today with science and technology. So that's it. I'm going to end you with one thing because it's Christmas. And this may not work because of the sound. It's a video. Well, we'll double check. This is classic. We're unplugging it and replugging it.
Turn it off. Is that what they do with data?
Yeah, that's what they do with data. It starts malfunctioning. So while he's doing this, are there any birthdays? How about now?
Yeah.
Yeah, I was going to ask, so while he's doing this, are there any birthdays? Wait, for real?
Why not?
Like today?
It's his sister's birthday.
Well, that so you ruined my joke, too, because then nobody was going to raise their hand, and then I was going to say, no, but it doesn't have to be today. All right.
Have they ever addressed the issue that when you transport down, what happens to the momentum?
That's a good question. I think we've transported people like flying through the air, and they all just come to rest on the transport. I think they cancel it out. Okay, we're going to see if this works. Everybody, hold your breath, cross your fingers and toes.
Oh, the weather outside is frightful. It's so delightful. And such sweet no place to go. Make it so. Make it so. Make it so. It doesn't show signs of stopping. And I brought me some tea Earl Grey hot. The hot way down below. Make it so. Make it so. Make it so. When we finally kiss, good night. Now, I hate going out in the storm. But if you... Really? Shut up, Wesley. All the way home, I'll be again.
Oh, the fire is slowly dying. And I hear...
We're still goodbye, then. But as long as you love me, so... Make it so. Make it so. Make it so.
Does anybody have any questions?
It was that good, huh?
Original series or next generation?
I was told I have to repeat the questions. Original series or next generation? I have to say next generation. I think I grew up watching that. I feel like whichever one you see growing up is the one you get.
So, does the technology change much between the different Star Trek series? Between the original down to, I guess, the latest one, which has come out this year? Does the teleportation, like in the movie Star Trek, they kind of tweak the teleportation so now you can teleport people that are moving, right? They had to be stationary, I think. Does the technology change at all between the movies?
So it does a little bit. It's interesting, actually. The main change, realistically, is that the production design changes. That everybody wants something to look cool in the new movies, so they change the way everything looks. And so part of that is the technology sort of. If anybody's watched the new show, they have these LCD screens and these holograms that they talk to, and it all looks very futuristic, what we'd consider now. But ostensibly, it takes place about 10 years before the original series, which is very much a 1960s science fiction, where there's all these giant levers and brightly colored panels, and there's no real LCD screens in existence. So the technology does change a little bit. It's mainly interesting to watch the production design change and just figure out what everybody thinks the future should look like. Like the 1980s, the Enterprise D apparently, the future was just going to be like a giant space Marriott or something. So, yeah, that's mainly it.
Any other questions?
So, what about the holodeck and all that?
What about the what?
The holodeck in the Star Trek Next Generation and all that. We're going to have some recreation, but it's sort of energy that's also sounds real. And
So Boris is asking about the holodeck, which, if you guys haven't seen the series, The Next Generation, is this room that you can go into and you get the computer to start some program and it generates this completely realistic scene. Like I'd say, like, go into the holodeck and say, put me in the Happy Valley Brewing Company, and suddenly it would just appear and there'd be all these people there. And you're talking about just like how the holodeck characters are sort of alive. But yeah. So the holodeck characters are controlled by the computer, and like in terms of like a strict. All right, I'm just gonna yell. So, all right, okay, maybe we'll do one more. This is the last question. So, right, so the people, the characters in the holodeck that are run by the computer are running around. They seem completely like regular people. They're intelligent. In terms of a Turing test, like, can you tell this apart from a regular person? You would not be able to. So, are those people alive? So, are those people alive? Right? Nobody ever talks about that. I feel like that's a good point, Boris. There's this weird, like, the Federation has this real blind spot for all their liberal, progressive leanings about their computers and their holodeck characters, where they're just, if the holodeck character annoys you, you can literally just say, like, computer, delete him, and he vanishes. And he doesn't exist anymore.
well, there's, I think they addressed a bit of that in Voyager. Because there's the holographic doctor that at some point goes into a trial.
Right, and somehow the holographic doctor gets a fair pass, but nobody else does.
Because he wrote like a novel, and there's the whole issue of royalties.
Right.
And so there's a trial, and I'm outing myself as an Italian that's puzzled by the US law system, because watching that in Italy, that was like, okay, it's the US, so obviously someone is going to sue someone else.
I feel like that makes sense, yeah.
There is another episode of Voyager where there's a planet where all the holograms are being hunted, and then all the holograms rebel, and it's like, well, wait, there's a computer program. Should we allow them to kill the real people? It's like this huge debate. I don't remember how it ends, but it's just...
So I just had a child in May, and it turns out that Star Trek Voyager is great to watch with a young baby, because I don't really have to pay attention all that much, like at 50% level. And so if he starts doing something, I can deal with him, and I don't really miss anything in the show. So I've watched a lot of Star Trek Voyager over the last couple of months. I have not gotten to that one yet.
Let's thank Tom one more time.